Okay, we have this genetic trait. X1 is the number of capital AA individuals in the population, where the probability of an AA individual is p squared. The probability of an X2 individual is 2 times p times 1 minus p, and the probability of an X3 individual is 1 minus p squared. So we know X1 is going to be the number of successes if the probability is p squared. We know X2 is the number of successes if I have n trials, and the probability of success is 2 times p times 1 minus p. And X3 is the probability, or is the number of successes, when the probability of success is 1 minus p squared. And these are not independent because we know full well that the sum of these three things has to be equal to n. So here is a random variable capital P, which is proposed to estimate whatever this population, this proportion P really is. Let's find the expected value of P and then the standard deviation of P. Well, the expected value of P is easy. The expected value of P is going to be equal to the expected value of 1 over 2n times 2x1 plus x2. And so splitting this up, that's going to be 1 over n times the expected value of x1 plus 1 over 2n times the expected value of x2. And I know what the formula is for the mean of a binomial distribution. So that's 1 over n times this expected value is going to be this number of trials times this probability of success times 1 over 2n times this number of trials times this probability of success. And so simplifying, we get p squared plus, over here, everything cancels. 2n cancels 2n, and I'm left with p minus p squared, which works out to be little p. So the expected value of capital P is indeed equal to little p, like it should be. So that's easy. The much more interesting and complicated problem is to figure out the standard deviation of P. Now let's talk about the strategy before I start computing this. So let's talk about the variance of P. The variance of P is going to be equal to the variance of 1 over 2n times 2 times x1 plus x2. So 1 over 4n squared times the variance of 2x1 plus x2. And then this is equal to the variance of 2x1 plus the variance of x2 plus 2 times the covariance of 2x1 x2. And I can simplify this a little bit. This is going to be 2 times the variance of x1 plus the variance of x2 plus 4 times the covariance of x1 and x2. Okay, now the variance of x1 I know. The variance of x1 is I can know from the binomial distribution, so that's straightforward. The variance of x2 I also know because that's binomial. What I don't know, at least I don't know it yet, is the covariance of x1 and x2. So that I have to figure out first. Once I figure this out, then I can plug in and then get the variance of P. So let me put this page aside and let's figure out how I'm going to get at the covariance of x1 and x2. The way that I will figure out the covariance of x1 and x2 is by looking at the variance of x1 plus x2 by itself. And that's the variance of x1 plus the variance of x2 plus 2 times the covariance of x1 and 2 from one of our theorems in class. And this part, the covariance of x1 and x2, that is the thing I'm trying to solve for. Now x1 was binomial, and so that is going to be n times its probability times 1 minus its probability. Likewise, x2 is binomial, so that'll be n times the probability, 2p times 1 minus p, times 1 minus that probability. Then I've got this third term that I need to figure out. And so the right-hand side simplifies pretty nicely. Now what about the left-hand side? To simplify the left-hand side, I'll use the fact that x1 plus x2 plus x3 has to be equal to n. And therefore x1 plus x2 has to be the same thing as n minus x3. And variance of n minus x3, I can ignore the n, so that's the variance of negative x3, which is the same thing as the variance of x3. And that's equal to this right-hand side. Now the variance of x3, that is also binomial. And so the variance will be n times its probability of success times 1 minus the probability of success. And so finally, I've got this big mess on the right-hand side where I have isolated, well, I haven't isolated it yet, but the only thing that's not known is the covariance of x1 and x2. And so I can solve for this. Okay, well, there's nothing to do except just do it. Let's see if I can simplify this a little bit. This is going to be n times 1 minus p squared. And in the parentheses here, I'll have 2 times p minus p squared. Here I have n times p squared, 1 minus p, 1 plus p, factoring out the difference of two squares. Then here I have 2np, 1 minus p. And what's left here is going to be 1 minus 2p plus 2p squared. And that's plus 2 times the covariance of x1 and x2. So if I isolate the two covariants x1, x2, and I bring everything over to the left-hand side. First off, I note that everything on every other term here, there's an n in it. Every other term has an n, and also has a 1 minus p. And also every term, I believe, has a p in it. So this has a p that I can factor out. There's a p here. There's an n, a p, and a 1 minus p there. So I can factor out an n and a p and a 1 minus p out of everything. What's going to be left here will be 1 minus p times 2 minus p. What will be left here, when I bring this over, will be minus. I have p times 1 plus p. And over here, I'll have 2 times 1 minus 2p plus 2p squared. And so 2 times the covariance of x1 and x2 will be equal to n times p times 1 minus p. All right, let's multiply out and hope for the best. We've got 2 minus 2p minus p makes minus 3p plus p squared. Minus p squared. Then minus 2 plus 4p minus 4p squared. And so let's see, how does it simplify? Well, p squared cancels minus p squared. We have 4p minus 3p minus p, and also 2 and minus 2. Well, that's nice. So all that's left will be 4n p to the third, p times this p squared, times 1 minus p equals 2 times the covariance of x1, x2. And so therefore the covariance of x1, x2 is equal to negative 2n p cubed times 1 minus p. Okay, so that's well and good. Now the next thing I have to worry about is to actually figure out the standard deviation that I wanted in the first place. The standard deviation that I wanted in the first place was the variance of p. And all that work, I've just figured out what 4 times, or what the covariance of x1 and x2 is. So, plugging in, 1 over 4n squared. Once again, I have the variance of x1. x1 is binomial, and so I know that's going to be n times its probability of success times 1 minus probability of success. And I should have had a 4 here. I apologize. It's a 4, not a 2. Here I have n times the probability of success times 1 minus the probability of success. And then I have 4 times the covariance that I just found. I found to be negative 2n p cubed 1 minus pn. So multiplying, we get negative 2n p cubed 1 minus p. Okay, now we simplify this and hope for the best. Now let's see, we start simplifying. So 1 over 4n squared. So 4n p squared, 1 minus p, 1 plus p. On this part, I have plus 2n p, 1 minus p. And then inside of this brackets, we've got, actually this bracket was fine, we have 1 minus 2p let's see, something went wrong, and it is, this 2 is incorrect. I apologize. So this is going to be 2p, 1 minus p. This is 2p, 1 minus p. Okay, so minus 2p, then here I have plus 2p squared. And then I have minus 8n p cubed 1 minus p. Okay, so let's simplify this. We have 1 over 4n squared. Now what can I simplify out? I can factor out an n out of everything. I can factor out a p out of everything. I can also factor out 1 minus p out of everything. What's left? I've got 4p times 1 plus p. So if I pull this, np, and then 1 plus p is left. Over here, if I pull out np and 1 minus p, what's left will be plus 2 times 1 minus 2p plus 2p squared. And on the last bit, if I pull out np and 1 minus p, that leaves me 8p squared. So that gives me p times 1 minus p over 4n. Let's multiply out. We get 4p plus 4p squared plus 2 minus 4p plus 4p squared minus 8p squared. Now, does this simplify? We get 4p squared minus 8p squared. 4p cancels 4p here, and I'm left with just 2. So I have 2 times p times 1 minus p over 4n, which works out to be p times 1 minus p over 2n. And so that is the variance of p. Therefore, the standard deviation of p will be the square root of that. So square root of p, little p times 1 minus p over 2n. And so this would be interpreted as the standard error when estimating the population p given the sample.